This week in class we're going to discuss the chemistry of substitution and the mechanisms that account for this particular chemistry. No matter whether we're talking about what we will call an SN1 reaction or an SN2 reaction, the following will always take place. We will have a carbon atom that is electrophilic. And because it is electrophilic, it will be bonded to a more electronegative atom. So I'm just going to simplify this as En. We will have a nucleophile. The nucleophile may be neutral. The nucleophile may be negatively charged. In this example, I will make it negatively charged. And I will replace the electronegative atom or groups of atoms with the nucleophile by substituting them. So now I have a carbon nucleophile bond and the electronegative group is now left with the electrons that it formerly shared with the electrophilic carbon. We call the carbon molecule that has this electronegative group the substrate. We call the electronegative atom or groups of atoms the leaving group. And of course, the atom or group of atoms that replaces the leaving group is the nucleophile. Now, we have discussed previously that there are 3 different scenarios that we can envision in which this process occurs. So really the differences in mechanism is going to be the order of substitution. And what I mean by order of substitution is what happens if we're to view this process as a movie. We do know that there are going to be 2 processes mechanistically that we're going to see over and over and over again. One is going to be loss of a leaving group. And the second is going to be nucleophilic attack. These mechanisms will be differentiated by the order of these 2 processes. And so we really have 3 choices. Choice number 1 is that we have nucleophilic attack first, and then in a second step, which is separate, we have loss of a leaving group. The second logical possibility that we have is that we have the loss of the leaving group first. And of course, remember, this would leave us with a carbocation intermediate. Then in the second step, we'll have nucleophilic attack. The third possibility is that both the nucleophilic attack and the loss of the leaving group happen simultaneously. That is, unlike the logical possibilities of step 1 and step 2, where you have a stepwise reaction, meaning we generate an isolable intermediate and then we react that intermediate to generate product. Logical possibility number 3 occurs at the same time or very, very close to the same time. In other words, the electron movement is synchronous and not stepwise. One of these possibilities needs to be rejected fairly quickly because of the limitations of our substrate. This substrate is an sp3 hybridized carbon. And so let's use this specific example, and I'm going to make this into a more specific substrate. And I'm also going to give it some stereochemistry. Now, after our unit on stereochemistry, we should be able to more specifically name this compound. This compound is going to be S2 bromopentane. It is S because if we look at our priorities, the low priority is oriented away from us. As we go from 1 to 2 to 3, we are moving counterclockwise. So S2 bromopentane. If we were to have a mechanism in which we had attack of a nucleophile in the first step, let me draw all the details. So we have a nucleophile that attacks and makes a bond. I hope that you guys can quickly see that this process is not going to be allowed for the simple fact that carbon is not present a pentavalent bonding environment. So this carbon would be bonded to 1, 2, 3, 4, 5 different types of environments. And we know, because carbon's a second row element from the science of quantum mechanics, that that simply is not possible. So we have to reject the first logical possibility as not occurring with substitution with an sp3 hybridized carbon molecule. Now, although this is not the main goal of this particular unit, let me refresh your memory that there is a type of nucleophilic attack and then loss of a leaving group that can occur. We will cover this more thoroughly in the second semester course, and that is nucleophilic acyl substitution. So if I have an sp2 hybridized carbon atom and I have a nucleophile, this process can be facilitated because the weak pi bond can be broken. This leaves us with a tetrahedral intermediate. And we have a good leaving group. And I hope what you guys see is that we have performed a net substitution where the chloride is the leaving group and our attacking species is the nucleophile. So when we talk about substitution mechanisms, we are not discussing acyl substitution. That will be formally discussed and covered in detail next semester. We are talking about alkyl substitution, and so we're limiting our argument to only sp3 hybridized carbon electrophiles. So let's take a look at one of the other logical possibilities. And I would like to begin with the logical possibility in which everything occurs at one time. So I'm going to start with a specific example. And I'm going to use the example of S2 bromopentane. And for my nucleophile, I am going to choose the hydroxide ion. Hydroxide ion is a pretty strong base, and as a result, it's a pretty reactive nucleophile. In this reaction, we will have a bond-making process between O and C, and we will have a bond-breaking process between C and Br. This follows the SN2 mechanism. What it means is that kinetically, the rate of this reaction is dependent upon the concentration of what we call our substrate, and also the concentration of the nucleophile. Because this slow step is the only step, the stoichiometry of the slow step becomes the rate law. It's first order with respect to S2 bromopentane. It is first order with respect to hydroxide, so it is second order overall. In fact, if we look at the vocabulary of SN2, the S stands for substitution, the N stands for nucleophilic, and the 2 means bimolecular. There are two molecules that collide in the slow step, or two molecules that react in the slow step. This does not refer to the number of steps. This refers to the kinetics of the reaction. Now let's start taking a closer look at this SN2 mechanism. And one thing I want you to quickly see from slide 7.4 is that the nucleophile is making a bond with the electrophilic carbon while the leaving group is breaking its association with the electrophilic carbon. In order for this process to occur, the approach of the nucleophile has to be anti to where the leaving group is. Organic chemists commonly refer to this as backside attack, and there are two very good explanations as to why SN2 always involves the approach of the nucleophile from the opposite direction with respect to the orientation of where this leaving group is located. Reason number one is that the backside carbon is certainly less hindered with electron density that the leaving group is going to occupy. And number two, you just don't have the orbital overlap because, again, you have a node between the molecular the atomic orbital of the carbon and the atomic orbital of the bromine. Whereas in the rear of the molecule, you have no such node. So there's a molecular orbital reason for this, and there's also a steric reason for this. More interestingly, what we find with regard to stereochemistry is when a molecule undergoes an SN2 reaction, the stereochemistry is flipped. Notice the orientation of methyl and hydrogen and ethyl before attack as opposed to after attack. I've commonly referred to this in class as inversion, like the prongs of an umbrella. Because we approach a nucleophile from the back side, once we get to the transition state, these groups, to facilitate the nucleophile, adopt a planar conformation. And then as this bond breaks and this back bond makes, we continue pushing these atoms forward. So if we have an S starting material, we have a net R product. It's not complete inversion, it is net inversion. So if I start with a pure S, I will obtain more R than S. Again, as I've continually referred to in class, life's just more complicated than what we do on paper. Now, to give you a better idea of what this looks like, let's take a look at the transition state. So when we push our arrows, notice the sulfhydryl is going to attack the electrophilic carbon. And as this bond begins to make, that is, look at the transition state, as this bond begins to make, the carbon-bromine bond begins to break, but notice the adoption of the three atoms that are bonded to the electrophilic carbon change their geometry, if you will, to a planar adaptation. In other words, we have a tetrahedral geometry in reactants, but we have a trigonal bipyramidal adoption in the transition state. This is a pentavalent carbon transition state. This is only stable for about 1/1000th of a second. So it's not making 5 bonds, if you will, but there are 5 areas of electrostatic density, one which is on its way to forming and one which is on its way to disbanding. Now, if we look at this with a little bit more detail and we draw a potential energy diagram, we'll see that these are not evenly made. For example, let's imagine that we have our S2 bromopentane plus our hydroxide ion Now, the driving force of these substitution reactions is almost assuredly going to be enthalpic because there's no real entropic benefit to the reaction. In other words, this should be an exothermic reaction. Of course, I'm showing the stereochemistry inversion. In the transition state, so here's our electrophilic carbon. The bromine is beginning to leave, so that will have a partial negative charge. Notice from the Hammett postulate that the transition state is closer in energy than the reactants, which means that the carbon Br bond is more bond-like than the carbon OH bond that's being formed. So these are not evenly spaced. There's more bond character with carbon Br than there is with carbon OH. And of course, we're tracking enthalpy as a function of reaction progress. Here's our delta H, which is less than 0, because it indeed is exothermic. So as we go back and look at our transition state, they're not showing this piece of critical detail. Keep in mind in these exothermic reactions that the carbon leaving group bond has more bonding character than the carbon nucleophile bond that's being formed. So when we say it's a simultaneous reaction, that's not exactly correct. We are breaking the bond more slowly than we're approaching the nucleophile. So it's not equitable between the two. So we say synchronous, but not simultaneous. Notice though the inversion is complete. So the methyl, the hydrogen are coming, well, the hydrogen's coming out of the plane, the methyl's going into the plane. And it's, you know, if you're approaching it from left to right, the methyl, the hydrogen, the ethyl are all pointing to the left. In products, however, after the bond is made, they're all pointing to the right. This will serve to completely invert the stereochemistry. In fact, let's take a moment to label this as R or S. So here's our carbon that's going to be attacked. And what I'm going to do is I'm going to do a rotation here to show these just a little bit more clearly. So the leaving group is pointed directly to the right, and the other three groups are going to be pointed to the left. Now we're going to start approaching the nucleophile from the back side. And as this begins to make a bond, of course, this bond is going to begin to break. That's with the arrow pushing methodology. Let's show it with the transition state methodology. So now the hydrogen in the propyl group and the methyl group, I know this doesn't look like they're planar, but they actually are planar. You have a backside approach by the OH. And then, of course, you have the bromide group leaving. So this, which was pointing to the left, is now planar. And as the bond completes itself, it will become pointing to the right. So at the end, I've made my carbon OH bond. And the other three groups have been pushed over to the right. Let's look at stereochemistry for a moment. In the reactant, priority 1, priority 2, priority 3, priority 4. Notice the hydrogen is not oriented away from us. So we're going to go from 1 to 2 to 3, which is R. Flip it, that is S. Now in the product, priority 1, priority 2, priority 3. Priority 4 is going away from us. We're going to go 1 to 2 to 3. That would be S. We flip it because the low priority is not oriented away from us, the viewers, and this is R. This is referred to as net inversion, and it is a hallmark of SN2 mechanism. So now the question becomes, how do we know when the SN2 mechanism will predominate? First of all, the SN2 mechanism is nature's default substitution mechanism. There are far more substitution mechanisms that proceed by this concerted reaction than by those that proceed by the SN1 mechanism, which we will explore in the next podcast. Second point is that it really depends on the nature of the electrophilic carbon. For example, we want relatively unhindered substrates so that backside attack is not going to be blocked. If we look at the relative reactivity, and we're going to set the secondary electrophilic carbon as our standard, so it has a relative reactivity of 1. Notice that the methyl electrophilic carbon has a relative reactivity of greater than 1,000. And the primary has a relative reactivity of about 100. But the tertiary is too slow to measure. Typically in organic chemistry, if we have a methyl substrate or if we have a primary substrate, it will always proceed by the SN2 mechanism. We'll get into more of the details of this once we complete the picture with SN1. But primary substrates, methyl substrates, will always proceed by the SN2 mechanism. And one of the really nice things that your textbook does is it looks at the free energy activations to really put a nail into this argument. So let's consider this particular reaction where we have methyl bromide and cyanide as the nucleophile. Of course, we have the familiar transition state. Again, this carbon-bromine bond should be closer than the carbon-cyanide bond that's being formed. It, of course, is an exothermic reaction. If I begin to look at a methyl substrate versus a primary substrate versus a secondary substrate, notice what happens with the energy of activations. The lowest energy of activation is the least hindered substrate. And of course, as I go from methyl to primary, it increases. And as I go from primary to secondary, it increases. And tertiary substrates are so slow, we effectively say they don't occur by this mechanism. And so this allows us to rank these substrates in order of reactivity. The methyl is the most reactive to SN2, and the tertiary is the least reactive to SN2. So this gives us an introduction into SN2 mechanistic thought. I'll expand more on this in class and on future podcasts. I will also be podcasting the SN1 mechanism. So, and we'll talk about this in more detail in class and do more examples in class as well.